Right, that's the different channel. Okay, so all right, people, singular value decomposition. It's all happening now. So this is a great point to reach in a first course on linear algebra, sort of a semester-long version at least, and puts many things together that we've requires many of the things that we've studied through the whole body of work here. And the first part will be, we have about 5 pages explaining how this thing works. And then we'll do 2 examples in separate episodes, and then tie everything together in the extremely exciting thing that is the fundamental theorem of linear algebra or matrixology, right? We've had a whole bunch of things in there. The big picture story, we're going to get a few extra important details. All right, here it is. Well, you can do whatever you want, but yes, ominous organ music. As soon as you open this page, it should. Or it could be happy times music. That's good too. Okay, so, right, this is written out here, but we've seen factorizations arise naturally when we solve linear problems involving where we can encode things with matrices, right? So we've got LU, big deal, right? So some permutation of A can be turned into a triangle times a triangle, lower times upper. A equals QR was another big understanding one. These help with what we started off with, simultaneous equations, which has an L missing, simultaneous equations. And I know there are various ways to say that word. And then we get to these beautiful things here. We had some others that I haven't really, the Cholesky decomposition. So decomposition or factorization, we mean the same thing. So diagonalization, beautiful things. And then there was this extraordinary thing if A was symmetric, right? So we're really interested in AX equals B, right? So this was AX equals B. And now we kind of want to put these things together. The eigenvalue stuff works for this problem here, right? So we get a new x, right? We're transforming x. That's good. It's n by n, of course. Right. So in this case, we've got an m by n, and an m by 1, and then an m by 1 in general, right? So we can have a rectangular matrix. This is an m by n, and I should get rid of this thing. This should be a to the power of k. That's been the way we've done this, right? So this is a to the power of k. Let's make that a juicier k. And this is same story. It's an m by n. M by 1, m by 1. So these are square matrices, right? Rectangular here. Could be square, but rectangular in general. Square only. Right, so these factorizations encode things. They do different jobs for us, right? And so all of them have some limitations. There's, right? They only apply to certain kinds of matrices. For instance, diagonalization won't work, right? It doesn't work. So there are a couple of things, right? So diagonalization, we're very excited about that. I mean, it just seems so great, but it has some problems, right? So we love diagonalization. But these things, okay, here are the problems. So A must be square. It must have n linearly independent eigenvectors, which can happen in principle for any n by n, but we're guaranteed that's the case if A is symmetric. And we might not get this great thing of the eigenvector basis, right? We transform this new basis, might not be orthogonal. That's fine, that's what the system is. But we really like orthogonality. So a couple of things. We like orthogonality, we like this kind of eigenvector story, right? Mapping from a vector to itself with just a simple multiple, right? Lambda. We also like I guess I should write that up here too. So yeah, A times V equals lambda V. It's these three things. That's a sad little V. Sorry. I feel a need to make this right. So this is yeah, just a V, right? I was solving those problems. Okay, so back to where we are. We like those pieces, but we can't have them, especially for rectangular matrices. So, right, we want to move back to AX equals B. We want to think about that and think of and see how we could use diagonalization there. So we're going to get to a factorization that will help us in a number of ways. I mean, it works for all matrices, and it will help us in particular with data compression or for finding the most important elements of a system. So for instance, an image, right? If you want to compress an image, maybe not an issue so much these days, but certainly, you know, if we're sending things from Mars or you're sending little pieces of, you know, information around, then you want to send the most important pieces. So it helps with that. It helps with finding the most important node or nodes within a network according to some sort of search problem, perhaps, if you like. So Google is involved here. So and I've listed a couple of here. So Supreme Court decisions, that's this network kind of thing. Pages on the web, building blocks of images. All right, so there are a couple of things, and we'll get to those later on. And so these are great. It's used all over the place. So think of finding the essential features of something, yes. And it will finish our big picture story, right? So we had this crazy thing. We're going to fill in some last few details about row space, null space, column space, left null space. There is a little more to add there. So, and this will be the fundamental theorem of linear algebra completed. Okay. So singular value, decomposition. Sometimes you'll see principal component analysis. It's used in many, many fields to find the most important things. All right. Okay. Okay. So let me put. I'm gonna have two examples. Some nutritious examples. Right. So all of this that I'm going to go through now, it's just the why everything works. Okay. And what we're actually trying to construct and why it all works. So this is the eigenstory. This is a beautiful thing. Right? Classic thing. So n by n, of course, is our matrix, so it's a limitation. May not have a basis, that's the sadness over here. And they're pointing in the same direction. Okay. So we're going to have to give some of this up to be able to use this with AX equals B. And, right, so we want to get to n by n matrices, so we have to give something up. And one thing we don't have, right, we don't have orthogonality. It's not ensured, right? So we want this. I'm not quite sure. I haven't explained. Monks will be involved, but we know that orthogonality comes from symmetric matrices for the eigenvector. So we'd love to be able to use that in some way, right? Orthogonal bases are the best bases. Okay, so I mean, there are some caveats, but basically that's good. So here's the new plan, this thing here. Let's make this big. We're going to think about real matrices, but this can be generalized. So, right, so that's this piece here. A is real. So we're going to have, instead of AV equals lambda V, it's going to be AV equals, and so this is a unit vector. Right, so let me make that clear. Unit vector. Another unit vector here. These are called singular vectors. We're going to, and this is a singular value instead of an eigenvalue, it's a singular value, right? New terms. So V is going to live in Rn, right? That's where the x's live, and we have B, AX equals B. B lives in Rm, that's where the u's will live. So it's the u's will form a very nice, an orthonormal basis for Rm, It'll be in particular an orthonormal basis, if you break them into two pieces, orthonormal basis for column space, and an orthonormal space for left null basis for left null space. The V's, right? So A times V, the V's will live in row space and null space, and will form an orthonormal basis for each, and then all combined will form an orthonormal basis for Rn. Okay, that's what this is saying, these next pieces. So let me just, right, so they're an orthonormal basis. They live, and here it is. They form an orthonormal basis for Rn, right? And the U's are in Rm, and they form an orthonormal basis for Rm. Right, column space, left null space, row space, null space. Good. Extra thing, these singular values, they are all positive. We choose them to be ordered from largest to smallest, very important, so we can talk about what's big and important here. And there are only R of them, where R is rank. Rank. Right, so this gets at the whole business that row space and column space have the same dimension, and that A really maps row space to column space, and it sends all of null space to 0, right? Maps it to 0, and if you like, left null space would be sent by A transpose to 0 as well. But there is a one-to-one mapping between row space and column space. There's nothing weird happens, right? No banana-shaped stuff. You're allowed to, stretch a little bit and so on, but it's all going to be linear. Rotation's okay too, but okay. So this is how AX will work. You have to come back to this picture and read it again. But we'll just sort of talk our way through it. So the idea will be, we're going to transform X into the V basis, right? We're just going to change its representation. We've talked about what this is. We're just going to change the representation. So then we'll have this matrix in the middle, a capital sigma matrix, which will send the V's to the U's, right? V1 goes to U1, and whatever's hanging on V1 gets sent to U1 and gets multiplied by the sigma 1, which is a positive number. So any rotations or flippings are really in how these bases are oriented relative to each other, relative to the overall spaces. And then the sigmas are just positive. So we're going to, and then once we've got them over here, we transform from the U basis back to the standard basis underlying Rm. So we lift from the standard basis to V basis, do the mapping over to the U's, and then back to the standard basis. Right. Okay. And that looks like this in terms of matrices. Yes. Singular value decomposition. It's real. It's happening. The monks tell us to believe. We believe. They really are. They're chanting SVD. Having a great time. So exciting for them. Okay. All right. Okay. So this is the business, right? So before we had things like, right? So of course we had A equals Q lambda Q transpose. Compare with this thing. Yes, it's all happening. So A is an m by n in general. Sigma in the middle, this is capital sigma, capital Greek sigma, is m by n as well, right? So these are the same shape, and that's what this is supposed to be here. Right, so here's an example. So just as U, for example, in LU decomposition is the same shape as A because it's really got A inside it, and L is a combining matrix. These two are transformation of bases matrices. They simply have the bases lined up in them, right? So it's going to be V1, V2. Well, we'll get to that. And so these are full, right? These are full of things. Let me stacked up like this. Again, this is m by n. So these are square, these two on the end. n by n, they're going to be quite different shapes, and n by n in the middle. And it's all zeros, except potentially for this line here in the middle. So it is the main diagonal, but now we're in a rectangular matrix. So what do these things look like? Monks are just telling us this is true, right? Okay. So U, it's this orthonormal basis for Rm. It's m by m. V is the orthonormal basis for Rn, right? It's where the x's live. Right? X lives here. The B's, the P's, the E's, Y lives here. We also wrote XR for row space, XN for null space, XP for particular, XH for homogeneous. That's the different worlds, right? And then we have this thing. The sigmas are lined up on the main diagonal, and then zeros here, right? So the main diagonal, it depends on the rank and m and n, right? That you know, it could be a square matrix, it could be uneven. M and n could both be greater than r, so that's how many zeros there are, right? But this isn't, right, here it is, m by, I need to highlight this. This is an n by n and m by n, right? So this is, let me write the words. This is the same shape as A. Very important, just to get this right. This means all zeros, right, here and here. So mostly empty, completely empty, except for R numbers. R equals the rank. Again, let's write that, very important. R equals the rank. I mean, you can imagine there's a sigma R plus 1, sigma R plus, there are these numbers, it's just that they're all zero, and they correspond to the V that gets sent to, that are in the null space, get sent to 0 by A. Okay, keep going. So let's see how this works. This is the sort of a claim that we can do this for every A. So we need to find out that this is actually true. So we're going to just line it up and say, okay, we believe this is true. We believe we can find a orthonormal basis for Rn and an orthonormal basis for Rm, and that there's a very simple transformation between them for any A, right? So there are two pieces here, right? The thing we've just written down, and that this corresponds to this story. So let's put these pieces together. Right, that A sends VI, the vector VI, to UI and multiplies by the sigma with this growth factor. Okay, so the monks, with the whispering and the chanting, say, try this business. All right, let's make their little statement a bit clearer. You know, classic monk stuff, they kind of giggle. Okay, giggling monks, never good. Okay, so let's try it. Okay, we're gonna try A transpose A, fine, okay? Now, first of all, we know something good about this. This is m by n. We've seen this little beast before, and this is n by m, if we include the transpose. So the m's match up, and this makes an n by n matrix. And we also know it's symmetric, right? We've got this before. So, so we know, so key thing here is that we know A transpose A transpose equals A transpose A, right? For any A. Doesn't matter what shape it is. Right? Symmetric. For all A. So that is huge. Symmetric measure, we start with A as being real, so this means we have an orthonormal set of bases made out of the eigenvectors of A transpose A. Pretty good. It's pretty good. Plus real eigenvalues. It's going to be one more little bonus, but let's get to that. Okay, so let's do it. We're going to put in this form that the monks have told us to believe in. So we get V, right? V, oh, I'm having trouble with that. V transpose, that's this piece, transpose, sigma transpose, and then U goes over here. U, oh, dear. U transpose. And here we just have U, sigma, V transpose, right? Yep, so this big transpose here did the work. And then this is the identity, right? Because U is made up of unit vectors. They form an orthonormal basis. So it's a U and V are both orthogonal matrices. Their inverses are just their transposes. U minus 1 equals U transpose. V minus 1 equals V transpose. Good. Because we believe. All right, so that identity just gets sloped together. This is V transpose transpose, which is just V. So now we've got V sigma transpose and then sigma. So these are these two diagonal matrices and then a V transpose here. So let's write out what this looks like. So the first part, okay, so these vectors are here, right? V transpose is here, boom. And then if we think about what this thing does, it is an m by n and then an n by m. So this is n by n. So it's square. So now this is square. It's diagonal. Looks good. It's got, because they're just sigma 1s, they multiply each other. So we end up with, the sigmas just multiply each other. So we end up with sigma 1 squared down to sigma r squared down to here, right? And then zeros after it, and zeros everywhere else. So this looks like, yes, it looks a lot like this. The monks are very sneaky. Okay. It looks exactly like that. So is this true? Well, we know A transpose A is real, symmetric, right? Real and symmetric. Therefore, the eigenvalues are real, and the eigenvectors do form an orthonormal basis. So in fact, the eigenvector, so if we diagonalize A transpose A, we will get these V's, right? We get these guys. So that works. We will get real eigenvalues, so that's pretty good. There's one more piece that we need to know, which is that we have to get positive eigenvalues, or at least eigenvalues that are greater or equal to 0. So there's some monk joy happening over here and just here. Yep, won't be quiet. Okay, there's a filter, a monk filter, which is very helpful. Okay, so that's almost there. This is augmented monk joy, and is why we kind of put in the PDM stuff. Let's construct this beast here, right? So we had this sort of form, X transpose blob X, yeah. So, one step here, right? So this is, we're going to take these pieces here and make, that's AX all transpose. And this blob here goes to here. This is then just, so these are two vectors, right? This is m by n, m by 1. So this whole thing is m by 1. Same here, this is n by 1. One needs a hat. Right, these are n by 1. So it's a vector in a product with itself, which is its length squared. Very nice. Squared. Which has to be, it's a length greater than or equal to 0. Right? Has to be true. Right, so this is length squared. Yes, just this has to be true. So it means that A transpose A is semi-positive definite. Just because of that A transpose A structure, you can show this, that it's the that this X blob X transpose blob X is always greater than or equal to 0. That means its eigenvalues are always greater than or equal to 0. And so we can do this thing. We can say, where we made this claim that we wanted the sigmas to be greater than 0, then it's okay, right? So that's what's going on here. There are these steps. It means it's semi-positive definite. Eigenvalues are all greater than or equal to 0. And therefore, we can say this. We can find their eigenvalues, take the square root, and we'll get a positive, and take a positive number. Right, so it's sensible. So the upshot is this. It's an important result. So we can diagonalize the A transpose A. We will find the sigmas. They're the square roots of the eigenvalues. Right, this business here. And the V's. So we're almost there in believing this is all doable and true. It's a semi-positive definite thing, right? All that work, there it is, just one little piece. Now they're saying AA transpose, AA transpose, AA transpose. Yep. Okay. All right, so we can do that too. So we can do the same kind of thing. Let's see. AA transpose, same kind of story. This is an M by N. Now this is an N by M. So these match, and the whole thing is M by M. Square, symmetric. That is quite nutritious. All right, so here's the transpose piece over here, so we'll work that in. So this is a U, sigma, just writing this piece out, V, transpose. Right, so we're going to get a V, transpose, transpose. Let's do that. And then a sigma, transpose, U, transpose. This piece here, transpose, transpose, that just disappears. Right, flip, flip. Identity matrix in here, multiply it all through. U, sigma, this is great. Happy times, sigma transpose, U transpose. So this looks a lot like what we got over here, except we've got U's, and instead of sigma transpose sigma, we've got sigma sigma transpose. That will still produce the same kind of thing, except now this is an M by M matrix. Right, this whole thing here is M by M. It will still have those, right? Still have non-zero sigmas along here, and then some zeros here, but everything else looks the same. We also need, so this is a little surprising. It should be surprising. They're giggling. Yeah, they're giggling because they think this is weird. So it means that the A transpose A and AA transpose, doesn't matter what A are, is what A is, have the same eigenvalues. That are, the non-zero ones are the same, right? They have zeros as well, corresponding to the null spaces, which is simply the dimension of the null space, or right null space, and the left null space. But the non-zero eigenvalues have to match up. They're the sigma 1 squared, sigma 2 squared, and so on. So, same idea. We can diagonalize A transpose. We'll find the U's that way. And we'll find the sigmas again, right? Again. So that's good, fine, but we only need to find one of the, we only need to find the v's or the u's, right? Because this equation here will help connect us, and ideally we find the v's, because then a times v, I mean that's really what we've got to do. We find the v's, a times v will give us u. Right, that'll be on the next. We'll have that up, that piece coming. Okay, so we need to know this. How do we know this is true? How do we know this is really true? That A, right, so we've said that they have matching eigenvalues. Wow, so how does this all work? Okay, let's try it. So we have this, right, A transpose A times the eigenvector V, the VI, is sigma I squared times VI, right? We have this story. The monks say let's play with this in two ways, so I'll just highlight those because they say go this way and this way. Right? These are monks again. So we know this is true, right? This is a real symmetric matrix here. We find its eigenvectors, and we're saying that the eigenvalues, we're going to call them sigma I squared. We know they're greater than 0, so we can write them as a square in good faith. All right, we can proceed in two ways here. One is to just use this fact that this is A times, all of this works here, right? This is just the eigenvector equation is just sitting there. Okay, let me say this again. We know this to be true here, and the monks suggest that we just take the left-hand side and pre-multiply by VI transpose. All right. So it's got that kind of feel of a vector here, square matrix in the middle. Right, let's see what happens. So if we just keep this piece intact here, then that's just the eigenvalue equation. We can draw the sigma squared out the front, and then we have VI transpose VI, which is equal to 1. Right? Dot product of unit vector with itself equals 1. So this is equal to 1. So this is just a number, which we expected, and it's sigma I squared. Okay. Okay. So, but if we play around with this in a different way and we break this piece off and then rewrite it, right? So it's VI transpose A transpose. We rearrange it, make it AVI transpose. Then we have this thing that a similar thing that we just had on the previous page, which is we've got blob transpose blob. So that's the length of that blob squared, right? This is a vector. This is a m by 1 vector, right? A is m by n, v is m by 1. So these things are true. So these must be true. Right? So these must be equal. We've gone in two different ways. So that's what this statement here is. That the length squared, right? The length squared, well, the length squared is sigma I squared. So the length of A times VI is sigma I. So what's going on? If you take one of these VI vectors, you take the third one, map it over into, so it's in Rn, you map it over to Rm, you get a vector. Right now we know it has length sigma I, so that's a start, right? So we have the right length. This is a very nice thing, right? So that's good. So that's one piece. We have, right, we're looking, it had to have this length if we go back up here. This is a unit vector, and this vector has length sigma I, so we've got part of it. We need to know that it now points in the UI direction. All right, so the monks say take that same blob here, but now multiplied by A, different thing. So we're going to multiply by A, and again go in these two different directions. So once again, we have that, right? This is using the eigenvalue equation. And we can draw the sigma I squared out. And then we have A times VI is all that's left in there. So it's number times a vector. Right? This is a m by 1 vector when it's multiplied through. It's a matrix times a vector, which is a vector. We can just regroup what's on the left-hand side here. So this part gets regrouped here. I think I should use a different color. All right, we'll just take the first two and regroup them. And then the last two are grouped by themselves as well. So now we have some matrix times a vector equals a number times that vector. You know what that means, right? No. Matrix times a vector equals a number times the same vector. Means it is, this vector is an eigenvector of that matrix, right? So that's what this next statement says. It's an eigenvector of, so A times VI, which is over an Rm, is an eigenvector of AA transpose. And it has this eigenvalue sigma I squared, which is to say, this rather amazing thing, I'm not doing this properly, which is to say that A times VI is proportional to UI. It is in the right direction. It is, right? AVI really is the same. It is an eigenvector of AA transpose with this eigenvalue, right? So sigma I squared. Okay, let me say this again. We already know that VI is an eigenvector of A transpose A, right? That's back over here with sigma I squared. Now we're showing that A times VI is also an eigenvector, but of AA transpose, right? This blob here, and it has the same eigenvalue. Wow, it's really nuts. Okay, good. And put these things together, then we know this is true. And we'll have to choose, there's a couple of details here. So one is we have to choose U's direction, right? Once we've normalized, then we have two choices, right? We can go this way or this way. We have to choose the direction to match AVI, so we have to be a little careful with that. Right, so that's this first statement here. So there is a slight freedom that we fix up because we want the sigmas. This forces makes sure sigma I is greater than 0. Right? And then this is a very nice thing. If we found the VIs, which is generally the way to do these things, then this is how you find your UIs. You don't have to diagonalize AA transpose. So you diagonalize A transpose A, gives you the VIs and the sigmas, and from that you can compute the UIs from the singular value equation. A times VI is 0, right, for all of the vectors that are of the V basis that are in null space, and the same for UI, right? Those UI vectors live in left null space, and A transpose A times them would be zilch biscuits. Okay. Good. So last thing. Let's look at this. For A equals A transpose, we had this beautiful story, right? We have that, we can diagonalize it in this great way, Q lambda Q transpose, and the Q has the unit vectors lined up in it, right? And they're the eigenvectors, they form an orthogonal basis for Rn. Very, very nice, beautiful thing. And we realized when we wrote this out that in fact, we could see A as a sum of, so A is n by n. We can see it as a sum of projection operators. And if we ordered the lambdas by their size, then we could put the sort of most important projection operator first. There's an important, okay, so they have this form. All of them have this form. V1, V1 transpose. So it's an outer product, and then lambda 1 here. And these are exactly our projection operators, right? So you project A times X. This first thing comes along and says project it into the V1 direction and multiply by lambda 1. Right? Just cut everything else off. The next one says project onto the V2 direction, which is at right angles because it's a symmetric matrix, multiply by lambda 2. Do all of those things and then add it back up. So this is a real little machine, right? It just splits it up, says, okay, here's your vector. Here it is in my representation of the eigenvector basis, which is a beautiful one, it's orthogonal. And I'm going to stretch all the different pieces and then put it back together. The whole is exactly the sum of the parts in matrixology. Good. So for SVD, it's a similar kind of thing. So here are the little patterns, right? Outer products. Right? They're all rank 1. Right? If you do row reduction on an outer product, you get a rank 1 matrix, R equals 1. For SVD, we have something similar, right? So because we have these orthogonal orthonormal bases, and instead of S lambda S minus 1 for diagonalization, we couldn't do it. We needed these very clear things. So, right, these are simple structures lined up in rows and columns. So if we multiply through, get this piece here, so there are lots of zeros in here. So we do this first multiplication here, right, and that'll give us sigma 1 times V1, sigma 2 times V2, sigma r times VR, and then lots of zeros. Right, so we're going to end up with this character here, this character here, this character here. And written out here, there are going to be R rows that are non-zero. And then there'll be, depending, so it depends on M, but there'll be M minus R rows of zilches, right? So just all these are all zeros across here. Okay, this is an M by N. And at the front, we had these U vectors all lined up. If we go through and multiply all these things together, yep, then only the first R of them will matter in that they're the only ones that will hit anything. But let's look at this pattern. So it's going to be this one outer product with this. So first column, first row, first column, second row, etc. Right? So this is using sort of advanced matrix multiplication methods. So we end up with, and the sigmas are just constants, so they pop out the front. We end up with these outer products weighted by the sigmas. Sigmas are all greater than 0. Sigma 1 is the largest one, and sigma 2 is less than or equal to it, and so on, so on, so on. These are all outer products. But instead of being V1, V1, they're now, U1, V1, right? U1, V1 transpose. So they're all outer products. So A is a sum of these little, right? It could be an M by N. It's a sum of these rank 1 matrices, and there are only R of them. And each one of them looks a bit like, you could imagine it looking like a piece of tartan, right? So if you think of an outer product, you could say take this column vector, and then you're weighting it by the row vector, right? So it's the same thing, but it's sort of fading in and out depending on the modulation. Okay, so a very gridded structure coming out. And there's a limit to what you're right. One of those by themselves can just really just look like a piece of tartan. Can't look like a frog or a banana. You have to overlay these pieces, and you start to get pictures. And it's kind of surprising. You only need maybe 3 or 4 to get a pretty good picture of whatever you're looking at. A person or a frog, like pictures of frogs. Okay, that's pretty weird. And so this is the same story, just written as a summation. There are only R of these things. right? That's this piece here. And each one has a weight, sigma I, and there's this UI, VI, outer product structure. So this is an odd thing. This can be done for every A. And it allows us to say, okay, we want A to be, we want to approximate A for whatever reason. Imagine an image, though. You know, you could say, let's take A, take a JPEG, approximate it, and take the most important piece, then the next most important piece, the next most important piece. Good. So it's a summing of outer product rank 1 matrices, and this is the diminishing sequence piece here, and the Scottish Tartan claim that I'm making. And so this is a SVD, has these very nice properties. One of them is that it makes approximation of large matrices rigorous, right? So there's a story we can use. It's used in weather prediction, used in all sorts of things. Anything with large matrix. And you can say we'll speak of the best, rank 1, rank 2, rank 5 approximation. Makes our calculations much simpler later on. So that is the story of SVD. I know it's exciting, and I hope you kind of see how everything is, how so many things have been involved to get this to work. We need to understand rank, we need to understand outer products, we need to understand diagonalization, and of course that's eigenvalues and eigenvectors. We needed to be thinking about AX equals B, and we needed to understand this kind of beautiful thing for symmetric matrices. We need to understand positive definite matrices and semi-definite matrices. But this is a great thing. So the next pieces will be working through examples, and then we'll put it together for the big story, which is the fundamental theorem of linear algebra. So, all right, there you go. It's a great thing to know, and well done for getting to here. All right.